For the classification, we have different models proposed by the researchers already. And here we can introduce a very classic, also very famous model. It's called support vector machine, or the SVM by short. I think someone who have been taking machine learning or the data mining courses before, you have learned SVM before, right? So support vector machine is a linear classifier which can find a hyperplane to separate two classes of data instances, like positive versus negative. And we can further adopt some more advanced techniques like codal functions to allow the SVM to handle the nonlinear separation of data instances, which will be beyond the scope of this section. And for the support vector machine, we have some basic concepts about data set. Let's assume we have a training set, which are labeled already. And we can represent a training set as a set. And inside this set, we have n different data instances. Each data instance covers both the features and with the labels. This is xi denoting the feature vector of a data instance. It covers like d different features for instance, right? And this is y is the class label we want to predict, or the target labels we want to predict. So for our setting, we can just use a very simple case of the binary classification as an example. In other words, this y will be labeled with value selected from either positive one or negative one. Positive one denoting a positive class, negative one denoting a negative class. And we want to build a model to separate the positive class instances from the negative instances. Okay. And the support vector machine finds a linear function parameterized by W and B. W denoting a weight, B denotes a bias. We know that a machine learning model is a mapping, is a function. How can we define the function for the support vector machine? We define it as follows. So given the W, B, these are the parameters of the model. Given a data instance, the feature vector X, we can calculate the inner product between W and X. We can define this Fx as a mapping first, right? In this way, we can get all the feature values sum up with weight denoted by W, right? And here we'll do the classification, right? And we want to classify the instances, and we want to get the labels for the instances. And we do a very simple version for the classification. We can predict the label by using a very simple function here, depending on the fx value. If this fx value for a certain instance, like xi, is non-negative, if so, we can classify this instance as a positive instance. However, given instance, if this fxi is negative, if so, then we can assign it as a negative label. I know it is very brute force, right? But we can take this one as an example. So in this way, we can define a mapping of a function to classify the instances into positive class and negative class, right? So how it can work? According to our previous descriptions, normally via the feature extraction, all the data instances will be in the feature space, right? And here we can take the two-dimensional feature space as an example. We have both positive instances and negative instances. The squares in blue color denoting the positive instances, the round in the red color denoting the negative instances, right? The data instances in the feature space, normally they are mixed together, and we want to classify them in the means we want to find a line to separate them from each other. This line can be a straight line or can be some curved line as well. Because here we are doing the linear model. Linear model means we can find a linear line or a straight line to separate the positive instances from the negative ones. And then the question will be, how can we define or how can we find this line to separate these data instances? Because given the data distribution, we can always find or we can always draw different lines to do the separation. Which one is good and why? And how can we find this good one to define the model? So in the feature space, when we draw a line, In other words, we are defining a linear equation, right? If we join 9 here, we are defining a linear equation. This equation actually is Wx inner product plus b equals to 0, right? You can follow this, right? And what is x? X is for any features, right? And what is w? W denoting the direction of this 9. This vector will be perpendicular to the 9, right? It denotes the direction of the 9. For different w, we can draw different lines, right? How about this b? This b denoting the bias, right? The bias or the gap, right? The bias of this 9 to the origin. So right now you can see why we define this mapping in this way as Wx plus b to define as fx, right? And depending on the location of the data instances above or below the 9, we can classify them as a positive or negative instance. So this 9 separation will correspond to these two equations we showed before, right? We define fx first, and depending on the values, we can classify them as a positive one or negative ones. This denoting this instance is above the 9. This denotes the instance is below the 9, right? Okay, then the question comes, even though we can draw this 9, we can decide different w and b, right? Then we have different options. Which one is the best? And how can we choose the best one? Right? For the supply vector machine, this model, we can provide you with some high-level ideas about how they find S9, how do they do the selection of the optimal 9 for the separation. Let's assume we can draw the 9 already. In other words, we can define a W and a B to make the equation hold, right? And we can define this 9 here. Besides 9, we can always draw some parallel lines to this one, right? And we can further push the parallel lines towards the negative instances, as well as one parallel line and push it towards the positive instances, until the line touches some data instances. Now this line touches this point, this line touches this point, right? This line touches this point, it denotes what? It denotes what? And we can define this 9 to be the h minus 9. We can define this one to be the h minus 9. And we can also represent this 9 as a formula. It denotes wx plus b equals to negative 1. At the same time, we can also manually define this 9 to be wx in the product plus b to be a positive 1. Right? You can follow me, right? And we have defined two 9 to assist us to find optimal ones. And by drawing these two parallel lines, we can define the distance between them, right? We can define the positive distance and negative distance. The positive distance denoting the line we are doing the separation together with the parallel line we are drawing here to assist us. Similar for the negative distance, right? How can we say a line is a good one? If a line can make its d plus and d minus as large as possible, then this line will be a good one, right? You can follow me, right? So if we can find one line to separate the instances, and we also want to maximize the gap between them, right? If so, then we can say this line we are drawing here is a good one. Okay, you follow me, right? Okay, then the question comes, how can we define the distance between two lines? I hope you still remember how to define the distance between two parallel lines. It will be very straightforward, actually. A distance between one point to a line equals to what? Given a line with a wx plus b, right, equals to 0 is a line, and given a data point xi, we can define the distance between xi to its 9 as what? As the absolute value of wxi in the product plus b over the L2 norm of its w, right? Its w is denoting a norm. We will define this later, right? In other words, we can define distance between a point to a line. However, remember, if we select this point on the parallel line as a 1 to help us define the distance, if so, we know for this point on the h plus 9, this term equals to positive 1, right? Right? In other words, if we define the d plus this distance between them, then this term will be equal to what? It will be equal to 1 over the L2 norm of its w, right? Right? Because we know for its data point, it can make this equation hold, right? And we can replace this term according to its equation, it equals to 1, right? And the distance between this h plus and 9 we are drawing will be equal to 1 over the L2 norm of w. Similar for d minus, right? Therefore, we have a distance between the gap between this h plus and h minus, right? It will be equal to what? It will be equal to 2 over the norm of w, right? You can follow me, right? In this way, we can define the gap between two parallel lines. So, based on this kind of intuition, we can define the objective function for this kind of problem. We are starting the classification problem, right? So, given a training set, we have all the training instances with xi, with features and labels. And besides maximizing the gap between lines, we also want to ensure the model can classify the instances in the training set correctly. So we also have to define a loss function for the support vector machine model, right? We want to ensure the model can classify them correctly. And we can compare the prediction results by the model versus the ground truth, versus their true labels, right? We want to minimize the difference between them, right? So by combining the loss term together with the margin term, we can define the final objective function of this SVM to be minimization of loss plus alpha times 1/2 times L2 norm. You will find that this one is different from the previous one, right? Because here we're doing the maximization. We want to maximize this term. It equals to the minimization of this L2 norm over 2, right? And if we are doing the minimization here, it equals to this one, right? And this alpha is a scaling weight because we are minimizing two terms, the loss term as well as the margin. We want to measure which one is more important, right? We have to balance between them. This is more like a balance parameter. And so sometimes we can interpret this one as a margin, the reverse of the margin, right? And we can also interpret this term as a recognition term for the SVM model objective function. You can follow me, right? And in this way, we're going to define the objective function for the support vector machine model to be trained. And by minimizing this term, we will be able to get the optimal W as well as B. In other words, we can get the 9 here, right? By deciding the W and the B, we will decide this 9 for separation of data instances. So you can see every problem will be, defined into a maximization or minimization problem instead in the final, right? So we have to optimize some functions and we can get the parameters. These parameters will be returned as optimal parameter for the model, right? Like the SVM model we are studying here.